Hello, everybody. Welcome to this next conference in the AI Colloquia. And it's my pleasure to present our invited speaker, very well recognized and leader in the area of probabilistic reasoning and logical reasoning, Professor Alan Darwich. He's a professor and former chairman of the Computer Science Department of UCLA. He has a master and PhD degrees from Stanford University, has served as editor-in-chief of the Journal of Artificial Intelligence Research and received the Lockheed Martin Excellence in Teaching Award. He's a fellow of AAAI and ACM, and he currently directs the Automated Reasoning Group at UCLA with his research interests in the areas of probabilistic reasoning, symbolic reasoning, and machine learning. He is an author of an excellent book in Bayesian Networks called Modeling and Reasoning with Bayesian Networks from Cambridge University Press. And a more personal note, I collaborated with Adam in the organization of UAI in Acapulco in 2003. And I remember he told me food is the most critical aspect in the conference. That's what people will remember. And I always take this advice into account in my next organizations. So welcome, Alan, and very nice to have you here.
Thank you, Enrique, and thanks for the organizing committee for inviting me to present at this opportunity. Today we'll be talking about tractable circuits, both arithmetic and Boolean, and their applications in AI and computer science more broadly. And let me start just with a picture first. So I put these two pictures, and here's a picture of a Boolean circuit, a picture of an arithmetic circuit. You're probably thinking, well, I've seen these, even perhaps in a digital logic course. So what does AI have to do with this? We will see. These are not just Boolean or arithmetic circuits. These are tractable in the sense they do satisfy some properties that makes them very useful for computation within AI, probabilistic reasoning, logical reasoning, machine learning, and even beyond to CS. So I'm going to start with some high-level remarks about these creatures before we go into the details, and perhaps by contrasting them a little bit or putting them in the context of neural networks. So all of these things are circuits. They're feed-forward circuits in the sense that once I have them, I want to use them, I will end up effectively just doing single passes through them. Once you're using these, there's no more complex algorithmic work involved. But there is a main difference is that while neural networks are typically handcrafted, these guys are compiled from models or from problems. So you usually have a problem, you want to solve it, and you end up compiling a tractable Boolean circuit or a tractable arithmetic circuit. And then once the compilation succeeds, you're pretty much done, because from there on, it's going to be just feed-forward evaluation or reasoning. And the notion of model here from which we compile these things could be quite broad, actually. We will see towards the very end, you can even compile the behavior of a neural network into a tractable Boolean circuit and then use this guy to reason about the behavior of that guy. So that gets pretty interesting, but we'll get to this later. So a couple of more high-level remarks. One of them is also guarantees. Because tractable Boolean and arithmetic circuits are compiled from models, we know a lot about them and their properties and how they behave and what they're doing. We know we have an issue with the neural networks in that regard because they're handcrafted. We really don't know what they're doing. We're trying to figure this out. And as a result of this, you'd see when we're studying tractable circuits, Boolean and arithmetic, there's quite a bit of computer science that gets involved there, algorithmically and on the theory side. In fact, we're going to start with a little bit of a review on that today. So the kind of math that gets involved in these guys is different than that, right? This is mostly optimization, is mostly algorithmic and basically computer science. Now, the other thing I want to mention is that these circuits, if you think that neural networks can be very large, these can actually get larger because they're synthesized typically. Now, sometimes people learn these from data, but typically they're synthesized, and when they're synthesized, they can get really large. In fact, we tend to fail in using them when we're unable to compile them because they get too large. So they can be quite challenging from that point of view. A couple of last remarks before we move on. Now, when you look at these two guys, you say, why do we need both? This is just Boolean. They're doing 0, 1, true, false, and these are arithmetics. They're doing, arbitrary numbers. Isn't this more general? Well, here's the interesting thing. We will find out that the real fundamental theories and notions and insights are all on the Boolean side. And the arithmetic circuits end up actually being almost implied. So this is where we're going to spend quite a bit of time on. And we're going to see that what we know about these and what we can do just follow pretty much easily from these guys, which is pretty interesting because that means we can really simplify the story because these are much simpler creatures. So these are the more fundamental creatures, the Boolean ones and the arithmetic ones attain their properties from these guys. The final remark I want to make here is you may have seen these under various names. So when I introduced these a couple of decades ago, I used arithmetic circuits, ACs. Later, the name sum product networks has been used, and more recently, probabilistic circuits. And it gets a little bit confusing sometimes because sometimes people use these to simply refer to a computation graph in which you have multiplications and additions, but sometimes they use them to mean computation graphs with multiplication and additions that satisfy certain properties. So we're going to try to clarify that later. But just one quick note here, even though these have been mostly used for probabilistic reasoning, they don't have to, right? So this is not just the only application for them is probabilistic reasoning, right? Okay, so here's the agenda. We're going to start with some quick basics that establishes some common grounds that we're going to use later, some concrete, some theory, and then we'll talk about Boolean and tractable circuits, and I'm going to sample some applications from probabilistic reasoning, machine learning, and explainable AI. Now, I'm going to be glossing over some of these concepts. Some I'll discuss in detail, some I'll just do them more broadly, but I will point you to my group's YouTube channel. It has a lot of material that elaborates on some of what I'll be talking about. All you have to do is on YouTube, just type UCLA Automated Reasoning Group, and you should be able to see it. And in fact, you'll see there a couple of my graduate courses, one on Bayesian Networks and one on the subject of this talk, Automated Reasoning. In fact, this is ongoing, so we're almost towards the last part of the course. All right, so let's get started here. And what I would like to do is two things first before I get into tractable circuits. First, I want to talk about some queries or some problems of interest in probabilistic reasoning that have been the basis for a lot of the work on inference. And I'll use Bayesian networks, which are a type of what people know more broadly as probabilistic graphical models. You can think of these as a compact way of specifying distributions. You have a graph like this one here. This is concerning some disease or a condition someone can have, and two tests that bear on that and their gender. And basically what you have with these is like a causal structure in the form of a graph. And then you have these what we call probability tables or conditional probability tables that gives us the probability of every variable given its parents. Okay, so it's very famous, very broadly used type of probabilistic models. And I'm going to quickly talk about four kind of questions that people ask with respect to these models. Now, the main point is they're called MPE, MAR, MAP, and SDP. The main point is these questions are of varying levels of difficulty. So there are complexity classes. Most people have heard of NP. There is PP and P to the PP, PP to the PP. And it turns out that each one of these questions, which are widely used, happen to be complete for one of these, meaning it's a representative of that class or the hardest in that particular class. And you'll see why we're doing this, because we're going to follow it also with a little bit of computer theory on complexity classes, very simple and short, just to give us the background we need to move on. So here's the first kind of question that people care about. And these are screenshots from a system called SAM-IM that's available publicly from my group. In this case, I went and told you, look, someone took the 2 tests for this disease, and I don't know the values, but I know that the 2 tests came out the same. They agreed. They're either both positive or both negative. And what you want to do is find the most likely state of these variables under that observation, and this is called the MPE, or most probable explanation, and it happens to be a person that doesn't have the condition, is a female, and both tests came out negative. Okay, so this is one query, and this happens to be NP complete. That's basically the hardest in that class. It's just like SAT in terms of difficulty. And when we talk here about these problems and being NP complete, we're talking about the decision version. So I'm not computing a number. I'm telling you, do you have an MPE whose probability is greater than something? So that ends up being a yes/no question. Okay, the other question is the bread and butter of probabilistic reasoning, where you're trying to compute the probabilities of certain events, like what is the probability that someone has a condition, and you're computing this number 45%. Okay, this is called MAR, and that happens to be PP complete. And here's the other question, which is known as MAP, which happens to be NPP to P complete. So we're getting more difficult. This is like MPE, but instead of finding the maximal value of all variables, the user chooses some variables. So we say, I want to know just the most likely state of gender and the condition, and you get this as the most likely state. It's interesting, when you maximize over all variables, it's easy, but when you choose a subset of them, it gets harder. And let me just mention one more query. The first 3 are very well known because they've been around for decades. They're in Yuda Pearl's book from the 80s. This one is more recent, about 10 years ago, called the same decision probability. It's a kind of expectation. It's kind of a value of information. Intuitively, I have a Bayesian network model. I'm using it like a classifier. I have a patient. I did the scanning test on them, and it came out false. The probability that they're pregnant is 40%. This is below a certain threshold, let's say 90%. So I'm declaring this person as not pregnant. The question is, what is the probability that this decision will stick if I were to go and collect more tests like urine and blood? So in this case, the STB says 78.7% chance this decision will stick, will not change, even if you go and observe these 2 guys. All right, so it's kind of a value of information question. That's the more difficult question among everything we looked at. The point is, these are very important queries. They're used all the time. And they have different levels of difficulty, and they correspond to these complexity classes. Now, what we're going to do next is show something pretty interesting. That if you look at these complexity classes and find what people call the prototypical problems for these classes, the classes that represent them, the problems that represent them, you'll find that they're actually problems on Boolean circuits. And I'm going to do them quickly. And there are going to be 4 of them, and they're going to correspond to these classes. The basic idea means, if you know how to solve these problems I'm going to show you next, which are all on Boolean circuits, you know how to solve these probabilistic reasoning and the many, many problems that also exist in these complexity classes. This is going to try to emphasize that if you figure things out at the Boolean level, and in particular with the Boolean circuits, you have basically figured things out way more broadly, and that gives you the sense of why these tractable Boolean circuits are so important, and they basically stand behind the way we do computations. So here's the questions on Boolean circuits. We have a Boolean circuit with 4 variables. It's going to be really simple. The first question, I think most people know what that is. I give you a circuit, and I say, is there an input for the circuit that will generate a 1? That is known as satisfiability. It's NP complete, and it's the representative problem for that. Second question is very simple. Now, instead of telling you, is there an input that will generate an output, are the majority of inputs such that they will generate a 1 output here, okay? And that ends up being called MASH SAT, and it's the representative of this class PP. This is the probabilistic reasoning. So here's the interesting thing. If you know how to do this, that is basically find if the majority of inputs to a Boolean circuit will generate a 1, effectively you have unlocked this class, and now you can do probabilistic reasoning. This gives you the beauty of complexity theory as far as simplifying things. Okay, the next two problems require that we split the variables into two sets, the inputs. And now the first question says, is there an input y? Can you fix these so that the majority of the z inputs are satisfying, will generate a 1? Okay, and that ends up being called EMASH SAT, and it's ends up being the representative or prototypical problem for this class. And you can probably guess what the last guy is. The last guy will say, okay, this guy says, is there a value of these under which the majority of these? Okay, this guy says, are the majority of the y inputs such that under each one of them, the majority of z inputs will generate a 1? And that ends up being MASH SAT, and it is the representative for this class. This problem, if you know how to do it, you can do expectations. You can compute expectations like same decision probability, all right? It gives you the sense of abstraction that if you can, again, if you're able to decide whether under the majority of y inputs, the majority, under each one of them, the majority of z inputs satisfy. Now, these are all decision problems, yes, no. There are what we call functional versions. Now you're wondering, how does this really work? And especially when I show you this picture, I tell you, look, if you want to solve any of these problems, I can reduce it. I can take it and convert it into a problem of this type. And if I solve these guys, I solve that guy. There's something missing here still. Where are the numbers coming in? These problems have numbers. Okay, because we've been focusing on what we call the decision versions. I'm going to give you two variants now of the problems I just talked about, which are called the functional versions, and they end up being the bridge with probabilistic reasoning and other kind of problems in computer science. So we said, for MASH SAT, we said, are the majority of circuit inputs satisfying, right? Out of 16, is the majority 9 or more generate a 1 output? Well, a version of this called sharp SAT, no, I don't want to ask you yes, no question. I want you to count them. Really give me out of 16, how many will generate a 1 output? Okay, now getting close. But one more addition, which really shows you the bridge between the two worlds, where now we're going to go and assign weights for inputs. So if the variable x0 is 0, I'm going to give it a number. And when it's 1, I'm going to give it another number. We call these weights. And the idea is an input now has a weight. So if you tell me 0, 0, 1, 1, I'm going to get the weight for this, the weight for this, the weight for this, the weight for that, and multiply them. And now I have a weight for the input. And now the problem is, give me the weighted count of circuit inputs that generate a 1. This is known as weighted model counting. So I'm counting how many inputs will generate a 1, but each one of them doesn't count as 1. It has a weight. And that actually ends up being the bridge to probabilistic reasoning. Now you can see, if you can do weighted model counting on these kind of circuits, why at least it's possible to solve probabilistic reasoning problems. And that is, this problem is very, very important. It's getting a lot of attention recently. It underlies this bridge between the probabilistic world and the logical world. In fact, while I showed these mostly on Boolean circuits, typically this is defined on Boolean formula, but it's the same. So someone would say, look, I have a Boolean formula like this, and here are all possible ways in which the variables could be set. And I have a weight for every one of these, which is a product of weights for the variable settings. Give me the weighted model count of this formula. That is, go to all instantiations that satisfy it and add up their weights, okay? So this paper is kind of the classical reference now on this area of weighted model counting and its connection to probabilistic reasoning. Okay, guys, so let's get moving now and start talking about tractable Boolean circuits. And the basic idea is that is pretty simple. If you have a Boolean formula and know how to take it and compile it into a Boolean circuit that satisfies certain properties, that is a tractable circuit, then you can solve these problems that we mentioned in linear time on this circuit. Okay, so I showed you a whole bunch of hard queries that are difficult in general. And I showed you that all of them can be phrased on Boolean formulas. So I need to just focus on Boolean formulas. And if I know how to do this, I can do other things. And the idea is, instead of solving these problems directly on this, I will compile them to a tractable Boolean circuit. And if I succeed, then it's going to be just feed-forward computation on the circuit. The secret is that these Boolean circuits have to satisfy certain properties. And each time you add another property, you unlock another complexity class, and certain computations that were hard becomes difficult, becomes easy. And what we're going to do next is just show you an example of these properties. And you're going to see they're very simple. And every time we add a property, we get a circuit type. It gets a name, all right? And you'll see if we add a couple of these properties, then we start being able to do probabilistic reasoning. So let's get through it. Everything in this theory of tractable circuits is based on what is known as negation normal form Boolean circuits. These have only ands, ors, and negations, but the negations only appear next to the input, all right? So you cannot have negations. So you have a layer of either direct inputs or inverters, and then you have layers of ands and ors after that. Now, this is not interesting. We're going to now add one property, and we're going to see that this property alone immediately allow you to do satisfiability in linear time and therefore solve MPE. Basically, it unlocks the class MP. And one of the things that you're going to realize here is how simple these properties are. This property is called decomposability. And when you put it in NNF circuits, you get a class of circuits called DNNF circuits. I introduced these about a couple of decades ago, and it's pretty simple. It says the following. In your circuit, go to every AND gate and look at the subcircuits that feed into it. And you want to make sure that these subcircuits do not share variables. So if you look here, you have LK, you look here, there's PA, and they don't share variables. And this has to apply to every AND gate. If your circuit, Boolean circuit, satisfy this, it becomes tractable, and it becomes called DNNF circuit. And you can now solve satisfiability in linear time. What does that mean? If you have an algorithm that knows how to take a Boolean formula and convert it to a Boolean circuit that has this property, that box can solve basically SAT, and it's as powerful as an P, right? Okay, let's look at another property now, which will give us the next class, PP, right? And this is called determinism. And when you have that property together with decomposability, you get a type of circuits called deterministic DNNF, very influential today, used all over the place. And that was introduced, this property and this circuit type, around the same time. And when you get determinism with decomposability, now you can do sharp SAT and weighted model counting in linear time. Now, the algorithm I'm going to show you in just a little bit also requires a property called smoothness. We're going to skip it. It's not as important. But let me explain to you what determinism first, and then we immediately see how we can use this to do interesting things. Determinism refers to OR gates. So if decomposability was about AND gates, determinism is about OR gates. And it simply says the following. If you look at the inputs to any OR gate, they have to be mutually exclusive. What does that mean? That means if you evaluate the circuit under any input, in this case, we're evaluating it where all of the variables are high. So red is high, blue is low. If you evaluate the circuit under any input and you look at any OR gate, at most one of its inputs will be high. So in this case, I have exactly one. For this OR gate, none of the inputs are high. So you can either have 0 high inputs or just 1, but no more. You cannot have 2 inputs that are high at the same time. That's basically what it says. Interestingly enough, if you know how to take a Boolean formula and compile it into a circuit that is decomposable and deterministic, now you can solve sharp SAT and weighted model counting. Now you have unlocked the class PP. Now you can do probabilistic reasoning. And remember at the very beginning, I said these end up being feed forward. Well, let's look at it. This circuit is over 4 variables. There are 16 possible inputs to this circuit. And I want to know how many of them satisfy the formula. It ends up being straightforward. You go to the leaves, and give every input a 1, except for this represents false. And then you just go through the circuit, you multiply, you add at OR gates, and you multiply at AND gates. You get the number 9. That tells you 9 of the circuit inputs will generate a 1, and the other 7 will not do that. Okay, so we just counted the satisfying assignment through a feed-forward pass through this, which is pretty remarkable. You can do a lot more interesting things. I'm going to mention this because it ends up being used in probabilistic reasoning. I have 9 inputs to the circuit that satisfy the formula. How many of them have A true and K false? You can also do this through a forward path through the circuit, and you're getting the number 2, which means 2 out of the 9 satisfying assignment has A true and K false. Now, all we did here is just changed how we feed the input by zeroing out those guys that conflict with this guy. Okay, this is called marginal counting. Okay, look how much we've gotten by 2 very simple properties, and you're going to see that these 2 properties underlie tractable arithmetic circuits and that world. Now, if you want to do weighted model counting, which is, I said, is the more practical one, similar story, but instead of assigning ones to the inputs, you end up assigning weights to these guys and just do the propagation and done. Okay, you have decomposability, you have determinism, you can do weighted model counting efficiently. And I just now want you to imagine a picture, because that's going to bridge us to the other world of arithmetic circuits, which I told you are just an implication of what we know about Boolean circuits. What did we do here? We were multiplying at AND gates and adding at OR gates. So think about it this way. If that's what I'm doing, I don't need the Boolean circuit. I can just look at this and suddenly I have an arithmetic circuit. And this arithmetic circuit is effectively computing weighted model counts. Now, you can still define properties like decomposability and determinism on these guys, right? Because these are functions of really these variables that are inputs. And now you can see how actually I can synthesize an arithmetic circuit from a Boolean circuit, and doing marginal counts on this end up giving you marginal properties. We're going to talk a little bit about this in just a little bit, but I just want you to see a picture in your head and to ground this claim I made earlier about arithmetic circuits being effectively, in a sense, a secondary concept compared to Boolean circuit in this regard. The other thing I want to mention is you don't just use these circuits by evaluating them. Sometimes you do other operations. They're still linear and through one pass through the circuit, but you do other computations. For example, remember the MPE, which is finding the most likely instantiation or the most probable instantiation in a Bayesian network. You can do this on these circuits, but instead of doing additions here, you do maximization. We introduced this in 2006 and showed how you can basically compute the maximum or the instantiation of the maximum probability through a forward pass. In this case, you can do a second pass backward, and you can identify that instantiation that has the maximal probability. Okay, I just have 2 more properties that I want to tell you, and that gives us basically another circuit type or 2 other circuit types on the Boolean level, and will be all we need to move on and talk more about probabilistic reasoning and the applications. This is also was an influential property called structure decomposability. It was introduced in 2008. It's popping up now again, and people are using it particularly with for arithmetic circuits. And the idea is pretty simple. Now, before I show it to you visually, I want to show it a little bit more algebraically. So the idea is every Boolean circuit represents a Boolean function. So what I want to do is I want to build a Boolean circuit for this function. And the way I'm going to do it, I'm going to split the variables of that function into x and y and decompose the function like this. So I'm going to have this function as a set of components, sum over the x, sum over the y. And I'm just going to repeat this process again and again. So I'm going to take now this guy and split its variables and decompose it like this. And by the time you're done, you will get a decomposable DNNF. But in this case, I want to impose one more constraint on you. I want to give you something called a V tree, which is just a full binary tree, and the leaves are the variables of the Boolean function. And I want you to use it when you're deciding how to split your variables. So when you are splitting the variables of f, I want you to use the first node, and these would be the variables in x, these would be the variables in y. So now you're going to decompose your function into components over b and components over a, e, c, d. And then when you go and recursively decompose further, like you're doing here, use now this guy. So now this is your x and y. Okay, and then you decompose this further according to the split of the variables. So the V-tree constrain how you do this decomposition, and then you get something called structured decomposable or structured DNNF or structured deterministic DNNF. And these now have to conform to a V-tree, a variable tree. And this guy actually does. So if you look at this AND gate here, and you look at the variables in the left and the right, they are conforming to this. The variables in the left coming from here, the one in the right coming from here, and so on. Okay? Important class. Once you have structured decomposability, you can do more things that you couldn't do before. But let me just do the very last property and very last circuit type here to end this segment. I'm going to add yet one more property. Now, if you look at structured decomposability, it was a strengthening of the property of decomposability. Now we're going to strengthen the property of determinism, give you a stronger version of it. So the same that we had, structured decomposability, I'm going to call these G components, I'm going to call them primes. I'm going to call the H component subs. So prime multiplied by sub, prime sub. And the additional requirement here is that these primes have to form a partition. They have to be mutually exclusive and exhaustive, right? So when you look at these guys, they are mutually exclusive and exhaustive. Now, that gives you determinism, but a stronger version of determinism. And when you have that, you get a new circuit type called sentential decision diagrams, or SDDs. I introduced these in 2011. And let's visualize it. These SDDs circuits, very important, very influential now, because you're going to see there is a probabilistic version of them, which has been used quite a bit recently. In particular, people have been combining this with machine learning systems, even ones based on neural networks. If you look at these circuits, you see that they're actually made of fragments that look like this, right? So you've got a prime sub being added, and then they're being disjoined. The fact that I have the primes as a partition, it means under any circuit input, precisely one of the G1, G2, G3 will be high, and the other will be low. In this case, this is the high guy, and the other two guys are low, which means that this whole fragment is effectively trying to decide, is it going to pass through H1 or H2 or H3? In this case, it's passing this particular guy. Now, these guys are called decision diagrams because you can think of this fragment as making a decision. Do I pass H1, H2, or H3? They're called sentential because they generalize the well-known binary decision diagrams, or which I'm going to show you on the next slide. These guys are a generalization, and these guys could be exponentially smaller than OBDDs. Let's just end this segment on this note. If you have sentential decision diagrams, if you can compile your Boolean formula into a sentential decision diagram, now you can solve MAJ/MAJ/SAT in linear time, assuming you use the right V-tree. This is the hardest of the problems. This is PP to the PP. This is the prototypical problem for competing expectations. So, guys, imagine how important this is. If you know how to take a Boolean formula and convert it into an SDD circuit, that box, that compiler, is a compiler or is an algorithm for competing expectations. And you've done nothing here except symbolic manipulations, which is important. Now, I skipped how you do E-MAJ/SAT. There was 4 of them. I showed you what property gives you SAT, what property gives you MAJ/SAT. There is another circuit type where I'm skipping that give you E-MAJ/SAT, and this guy give you sentential decision diagrams. Now, I'm going to skip the relation to ordered binary decision diagrams. We can get to this during the discussion if people are interested in. But in a sense, this is pretty important because these generalized decision trees, but we can talk about this later. Let me just say a couple of words here to move on. This area that I just mentioned, the notion of tractable circuits, what properties, what can you do with them, what happens to their sizes, is also studied under the term of knowledge compilation in AI. And the very first paper that in a way started this area was again from 2 decades ago. Just last year, there was a workshop, 5-day workshop in France dedicated to this subject. On my YouTube channel, you'll see the featured video is a tutorial I gave early in the summer at PODS, the Database Theory Conference. And there is a attached paper, which I think I cited earlier, which gives you a survey, a modern survey, including knowledge compilers and various tools, so you can see it there. And we're not going to talk about knowledge compilation. We're not going to talk about how do you really take a Boolean formula and compile it into a circuit of an appropriate type, except to say 2 things. There are 2 types of compilers called bottom-up and top-down. And the class that I'm teaching right now, there's already 2 lectures, one on each. If you go to the UCLA Automated Reasoning Group webpage, you can get more material on this particular thing. But this is pretty important. And last remark here is there's been a lot of interaction between this area, not just with AI, but database theory, communication complexity, and so on. So you'll see a lot of titles these days about knowledge compilation meets X. So knowledge compilation, tractable circuits, basically the same area there. Okay. Now we're going to go and talk about some applications. And we'll end up introducing more probabilistic reasoning applications, and we're going to see more types of circuits, just one more type. But I'm going to start by the following, because in a sense, this kind of started it all, which is if you have a Bayesian network and you want to ask one of these questions that we mentioned, MPE, computing marginals, doing map, doing SDP, how do you use it using this approach? Well, it turns out to be pretty straightforward. You take your Bayesian network and you can reduce it into a Boolean formula with weights. So you reduce it into a weighted model counting problem. And that turns out to be very simple, as I'll show you next. Now, if you do that, what does that mean? That means if you can do weighted model counting on this formula, then you can actually do probabilistic reasoning there. And how do I do weighted model counting? Well, you can compile it into a tractable circuit that has these properties, because that allows you to do weighted model counting. And we've seen when you do weighted model counting on that, you're effectively just evaluating an arithmetic circuit. So what happened here is you compiled a Bayesian network into a tractable arithmetic circuit. And if you have this, you can do reasoning on this in linear time. Okay, this is for computing marginal probabilities. We've seen if you do maximization, you can do MPE. If you want to do SDP, you have to do a little bit more, but you get the idea. These are circuit compilations of models that allow you to do very difficult things in linear time if you succeed in compiling. Okay, now I want to make a few remarks here. One of them is this idea of going from a Bayesian network to a Boolean formula is straightforward. I'm going to, at least the vanilla version of it. I'm going to show you a slide next. I'm not going to explain it, but just to give you a sense of how simple it is. And then I want to say a little bit more on these guys. Okay, here's a Bayesian network. And these are the parameters. It specifies this distribution. Again, this is a cartoon. I'm not explaining it. You can go to the POTS tutorial for details. Here's the Bayesian network. Here's the distribution it specifies. I'm going to go and effectively for every one of these parameters end up writing a Boolean sentence. And I'm going to get something that looks like this. This is my Boolean formula. It can be generated in linear time. I'm going to assign weights to the variables or their negations in a straightforward way. These are now the probabilities from your Bayesian network appear as weights for some of the variables. And now you have the guarantee that if you want to compute the probability of some event, that's the same as computing the weighted model count of this knowledge base together with that event. The point is you can take a Bayesian network model and write out a Boolean formula. And as long as you set the weights carefully, you get this picture of reducing to weighted model counting. Okay. And this is the vanilla flavor reduction. There are more effective reductions, but you get the idea. Now I want to mention a couple of interesting things because some interesting development happened after that idea. So When I introduced this initially, the idea was take a Bayesian network, write a Boolean formula, compile it into a circuit, and then you've got your AC, which is effectively decomposable, deterministic, and smooth. Now, two things happened after that. One of them is the idea of, well, if these guys are so great and I can do inference by just forward pass on them like neural networks. In fact, in this paper, I also show how I showed how you can use back propagation on these guys to compute the derivatives, partial derivatives, so you can train these in a supervised fashion if you want. The idea was, if these guys are so great, why learn a Bayesian network? Because people try to learn a Bayesian network and then compile it to this. Why don't I learn this directly from data? So this was in 2008. So let me learn these guys from data, learn arithmetic circuits from data. And then a few years later, something else came, which was interesting. It's not exactly stated that way in that paper. This is a more recent understanding of that paper, which is the following. What if I drop determinism and I do not actually use this and I just get decomposable and smooth? That type of circuit was called sum product networks. Okay. Now, according to what we discussed, that shouldn't work. If you just have the decomposability and smoothness without determinism, this should not be able to compute the right distribution, and it doesn't. But the observation, again, the way we understand it now, is that this guy still, if you apply the algorithm I showed you earlier for evaluating this guy, will still compute consistent marginals. So it is computing some distribution. It's not this guy, but some distribution. But who cares? If I'm going to be learning these from data anyways, I don't have a reference Bayesian network. I'm not going through this pipeline. I'm just learning these things. So if I'm learning them and they already compute a distribution in a tractable way, I'm done. And it turns out that, yes, so with decomposability and smoothness alone, you can get these to compute distributions, and these are known as sum product networks. And that was actually a big idea. Now, the interesting thing is it gets a little bit more interesting, because when SPNs were originally introduced, the claim was that not only would these compute marginal probabilities, but they will also compute MPE, most likely instantiations in linear time, using the algorithm I showed you earlier about maximization. And that turned out to be not correct. If you lose determinism, yes, these guys continue to compute marginal probabilities, but you can no longer use them to compute MPEs. Actually, that's NP hard. So later people said, let's add back determinism, but instead of calling this ACs, they call them selective SPNs. So selective SPNs are basically just decomposable, deterministic, smooth. This is the kind of more interesting creature that doesn't have determinism. Now, this paper, which is relatively recent, goes over the history of arithmetic circuits and what happened, and it's actually have quite a bit more interesting observations, so you may want to check it. And as I said, beyond SPNs and AC, people now also refer to these as probabilistic circuits. Typically, they are computing probability distributions, but arithmetic circuits that are tractable do not need to be computing probability distributions. They could be doing other type of functions beyond probability distributions. People get confused and they ask me all kinds of questions about the relations between these things. And I say, if you really want to get this story straight, think about properties, right? We know what the properties are. They're all at the Boolean level. And if someone talks to you about a circuit type, just ask first, what properties do you have, right? And, and that gets you through the different terminologies that people are using. And, okay, just to say that this is actually not just a theoretical exercise. These reductions and compilations, systems based on this were actually used in competitions, and they were award-winning. So let me see. I'm going to now talk about, move further into applications and talk about something very recent, actually, within the last year, to give you a sense of the use of these circuits as well. And this is under the label of model-based supervised learning. So now we're going to use these more like neural networks to learn from labeled data. And the idea is that if you have a graphical model like this, and you tell me, look, I'm always going to observe the values of A and C, and I want to compute the probability on B, you can compile a circuit that just does that, okay? This circuit, the output is the distribution, which you can use for classification, perhaps. And the inputs are your evidence and these parameters that come from the Bayesian network. Now, I do know the structure of the Bayesian network. I don't know the parameters. I want to learn them from data. And you can do that. You can train this using gradient descent. And the interesting thing about this is I can inject knowledge into this. So I can tell you, I know that when A is true, C must be false. And then that means I know the value of some of these parameters. So I don't need to train them. And you can inject other kind of knowledge. And now you have something that looks like a neural network, except I can inject knowledge into it. And recently, in a paper that came up in ECI, I showed how you can actually, with this compilation algorithm, you can compile these into tensor graphs, very efficient tensor graphs that are almost based on just matrix multiplications, so that you can train these in systems like TensorFlow and so on easily. You can see that paper, remarkable speed ups. We're talking about circuits that have tens and hundreds of millions of nodes being evaluated extremely efficiently. Check that paper out. And recently we used it to show promise of this notion of model-based supervised learning. So I'm going to quickly show you these couple of experiments. This also appeared recently. Vision is perhaps not the best domain for this, but in this case, we were looking at two types of synthesized shapes, rectangles and 7-segment digits, for which we know how to build models. And the idea is you have noise, right? So this is the rectangle, the original rectangle. I have noise. I want to recognize the digits or properties of the rectangles. And in this experiment, to illustrate one point, there was two types of noise: horizontal, like these 2 pixels, and vertical, like these. Okay, so the idea was, I want to solve this problem in 2 ways. I want to build a CNN neural network, which is, the best solution in these cases, and I want to do it in a model-based fashion. I want to build a model. So for rectangles, the model is pretty easy. It has an upper left row and column. It has a height and width and shape. ... You can build a very good model for this. It's a simple concept. And then I'm going to tell you, look, I know the pixel values and I want to predict the height or the row. So go compile an AC for that. And we did. Now you have 2 types. You have CNNs and you have ACs that are compiled from these guys. And I'm going to train them on these labeled images in a supervised fashion and see what happens. And we did it 2 ways. One is compiling the model without injecting background knowledge, because in these cases, I know that some of these variables are related in a functional way to their parents. So I had 2 versions, BN without background knowledge, BN with background knowledge, and CNN. And look what happens, pretty interesting. When you train on horizontal and test on vertical, or train on vertical and test on horizontal, this CNN was doing great under a normal setting, almost 100% accuracy, right? These are pretty easy problems. But when you try to do something like this, it basically fell apart. The guy with background knowledge was doing basically consistently very well. That gives you the power. I mean, it shouldn't be surprising, right? Because the AC that is being used here knows what's going on, knows what a 7-segment digit is, knows what a rectangle is, has a lot of knowledge. So it cannot be easily fooled by playing games like this one. Of course, the model for the 7-segment digit is way more complex than this, but that gives you the idea. This was another example showing how much data do you need? And you can see this guy really needs very little data to reach certain levels of accuracy. They eventually catch up with enough data, but again, shouldn't be surprising. It shouldn't be surprising, but has not been as illustrated, at least in this context, before. And part of the reason we were able to do this is this new compilation algorithm and compiling it into tensor graphs that can allow us to do this training easy. These circuits were really large, and we could go only to a certain size of images. We can't scale like CNNs can, right? So this is kind of a proof of concept kind of thing, because these circuits are really large, and they're more challenging in a sense than neural networks. There is a new class of circuits called testing arithmetic circuits. I'm going to just flash the screen here. I won't be able to talk about them because I don't have a lot of time left. But they're meant to bridge the gap even more between ACs and neural networks. Let's see. I do have only 10 minutes, and I have two segments. Each is 10 minutes, and I will have to skip one of them. So I'm going to skip this one, which is, and go to the last part. This, in a couple of words, is doing learning from data and knowledge, but in an even broader setting where you may have, there's no Bayesian network involved now. There is just data and some background knowledge. In this case, you have a department that's teaching 4 courses. You have data on what students have taken, and you want to learn from both data and knowledge. The knowledge is constrained. So the idea is, if normally you would be learning a distribution over all possibilities, but because I have knowledge, a bunch of these possibilities are ruled out, and I want to learn only over the feasible state as defined by my logical knowledge. You can do this using something called probabilistic SDDs. You compile your logical knowledge into an SDD circuit. You can parameterize this, and you're guaranteed to induce a distribution over only those satisfying assignments of the Boolean circuit. This is a very structured and principled way for inducing distributions over only those feasible states of the world. Since we have time for discussion later, I can come back to these. My course just had a couple of lectures on this last week, so you can get like a few hours on this subject if you want. But I'd like to move on to get to the last part because it's a little bit different than this. And just to tell you, very well behaved representations, and they've been used for large scale problems. In this application, maps were compiled into SDDs, and then GPS data was used to learn distributions over routes of how people can go from one place to another. And this was used to do things like route completions and distinguishing drivers based on their route behavior and so on. There's more developments there, a circuit type known as conditional PSDDs that is particularly suited for computing conditional distributions. And there is this notion of a structured Bayesian networks, hierarchical maps, again, discussed in my class if you'd like to learn more about these. But I'd like to go now for the last 10 minutes or so and talk about the last segment. Okay. Okay, in the last 10 minutes or so, this is very recent, last 2 years, where tractable circuits are being used to reason about the behavior of machine learning systems. So I'm just going to give you the gist of it and to see how powerful this idea is. And it's simply the following, that if you have a machine learning system like this one, which is a naive Bayes classifier, even though these systems gets used like you give me things like I have a patient, urine test, blood test, you compute the probability on pregnancy, check against the threshold, and then you render a decision. Even though the system is numeric, and even though it's learned from data, and even though it does probabilistic reasoning to actually compute a decision, it is nothing but a fancy way to specify a discrete function. Because if you look at it as a box, the input is a discrete instance, the output is a decision. So I can actually capture that input-output relation symbolically. I don't need probabilities for that. Now, I need them to generate that kind of discrete function, but I don't need them in principle. And indeed, in this case, you can go and compile this machine learning naive Bayes classifiers into a decision graph and something specific called an ordered decision graph. In the sense, if you give me an instance, I can go and simply follow the routes here in the usual way like you do in a decision tree, and I get here a decision. No, guaranteed, if you were to do the same thing on this guy, the decision on this instance will be exactly the same. It will be a no. So for every instance, these two guys are guaranteed to make the same decision. This is a very powerful idea. Of course, it doesn't always work. You need to have classifiers whose inputs and outputs are discrete, but that's actually captures quite a bit. And that's a big idea, because now you can say, well, what else can I do this for? Can I just compile naive-based classifiers or other things? And do I just need to get it into a decision graph, or I can compile it into other type of circuits? Well, yes, you can, depending on what you want to do later. And what can I do with these symbolic representations? So just a little bit of furthering on this. And once more, my course has actually, in fact, we just did this yesterday, I believe, the lecture on explaining decisions. Okay, you'll see that this was applied to benchmarks in the literature. This is an actual classifier from Stanford Medical Informatics. It was compiled into a graph that only had 156 nodes. So what can you do with this? And I'll give you an example of this, but let me tell you, a lot of this has been happening over the last couple of years. The basic idea about compiling, as I mentioned, is actually from 17 years ago. And you can see recent work on this. For neural networks, it's really very, very limited type of neural networks, but that illustrates the concept. Just want to give you one example application here before we finish this. You can explain decisions. And one of the ways to explain decisions is this notion that we introduced called the PI explanation or sufficient reason. So the idea is you give me an instance, it has 100 features or 100 characteristics, and the box, the machine learning box says, admit this person. It's a box for admission. And then you say, why did you decide to admit that person? So even though you have 100 features, the PI explanation or sufficient reason will bring you back a subset of features that are sufficient to trigger the decision. So I may point to 7 of them out of the 100, and I say these 7. As long as you fix these 7, this classifier will maintain its decision. Doesn't matter how you change the other guys. And this set has to be minimal. No subset of it will have that property. Initially, we called this PI explanation. More recently, we call it the sufficient reason. And for this classifier, you could say like somewhere like Sally tested negative for both scanning and blood, and blood and urine. And then it's declared as not pregnant, and you say why? And then it comes back saying because the scanning test and one of the blood and urine tests came out negative. I don't need all of these to be negative. I just need scanning and blood or scanning and urine. There are 2 sufficient reasons in this particular case. Now you have to understand, this came from a numeric machine learning system and now able to do symbolic reasoning about a numeric box using tractable circuits, okay? That's pretty powerful. You can use this, in recent work showed how you can use it to reason about decision bias. This is where you have some protected features and you don't want the classifier to use them. Now, there's a fine distinction here between a classifier being biased and a decision being biased. Now, the classifier may be using protected features, but when it made a specific decision on a specific instance, it may have not used those protected features. So there is a definition for decision bias, which is different than classifier bias. And it turns out that you can actually reason about decision bias also efficiently if you have compiled your machine learning system's input-output behavior successfully into a tractable circuit. We don't have time to go over the details. I will have to basically conclude soon, but let me just mention one quick thing here. In this recent work from that appeared last summer, there is the notion of a reason circuit, which is like a tractable circuit that's generated per decision that kind of gives you everything that went behind that decision. And then you can use it to start reasoning about the decision, including explaining it, including whether it's biased or not, and so on. Very exciting stuff. Now, let me just end with a couple of slides. This is part of a broader agenda about reasoning about the behavior of machine learning systems. Initially, we started by talking about explanations. Using this approach, you can do also robustness and verification. I didn't talk about these. Initially, we started by talking about graphical models, starting initially with naive-based classifiers. The list has been expanding as far as what can be treated. You don't need to compile into OBDDs. You can compile into other type of circuits. It all depends on what do you want to do after you finish the compilation. This is an example of a small neural network for telling 0 versus 1, which we managed to compile and then use it to do explanations. Look at this. It says, you give it this image and say, what is that? And it says a 0, and you say why, and the sufficient reason or the PI explanation end up generating 3 pixels. It's basically telling you, as long as these 3 pixels are white, you can do whatever you want with all of the other pixels, and I'm guaranteeing you I'm going to still classify this as a 0. Well, you can go and do this. And based on this explanation, I guarantee you this neural network will classify this as a 0, not as a 1. Okay, it gives you an idea of what's going on. So, powerful idea. And the idea is reason about what was learned. Sometimes people think of logic as a competitor with machine learning or with probabilistic reasoning, because at some point we thought we can use logic to build the systems we want in terms of capturing knowledge about the world. And then people found out that no, perhaps they're not as robust. They don't capture things as well as numeric systems, and it's better to learn instead of to encode knowledge, perhaps, right? So in fact, the evidence now suggests that we're able to do more by just learning. But that's a simplification of the role of logic, right? So in this area, we're using logic to do meta-reasoning. Fine, I'm not going to use it to encode your knowledge in this area, but you learned this thing, but I'm going to use it to reason about what you just learned, okay? So that is basically doing this. And of course, you don't have to do this just using tractable circuits. You can do this using other type of logical formalisms without compilation by, for example, using SAT solvers. You get less but more scalability. And I'm just gonna, end my remarks on this point here. And I have to stress, everything boils down to compilation. Being able to compile these circuits is the secret, is the reward, is where we need more people to work on this. And if you go to the POTS paper, which is the most recent survey on all of this, the title of that paper is 3 Modern Roles for Logic in AI. And it actually goes with this tutorial on my YouTube channel. You'll see a lot of citations, including to source code of compilers and so on, if people want to work on this particular area. But I think I'm done here, and I wish to thank you, and I am happy to take questions. So. And I see only questions in Spanish. Comments.
Okay. I'll try to translate.
Okay, so what do you want to do? How are you going to do this?
I can read the questions. And,
okay.
If translate if necessary.
Absolutely.
Maybe start with this one. How do you know if a circuit can be compiled?
Now, in principle, every circuit can be compiled. The question is, will you be able to do this in terms of being able to store it? So it may be too large that you cannot store it. In some cases, we can give you guarantees in the sense of, depending on the problem and its structure, I can look at it and sometimes say, yes, I guarantee you this can be compiled. And that happens, for example, in Bayesian networks. When I have a Bayesian network, depending on the topology of that Bayesian network, I may be able to look at it and say, I guarantee you I can always do this, okay? So there are sometimes, we are able sometimes to guarantee compilability, but not always. The problem, for example, with Bayesian networks is, as an example, but this applies to other problems. Sometimes I may look at the structure and tell you, oh, this structure is too complex. I did some analysis on it and I cannot, but that may not be true because it depends not just on the structure, on the parameters. And we've seen situations where based on structural considerations, things look difficult, but when you look into the finer grained details, they end up being easy. In fact, that's one of the main distinctions between this approach and other approaches. They know how to take advantage of these finer distinctions. I hope this answers the question.
Okay, thanks. There's another question, but I really don't understand it. Is they're talking about electric circuits are using most in robots or PLC? I think they are talking about another thing. I don't know.
Right. So I see a question
okay,
that.
I'll go to the next one.
Okay, go ahead.
I go to the next one. You mentioned that your methods can be applied to some neural networks. Which ones?
Right. So the ones we actually tried are binary neural networks. So these were, okay, I'm putting the picture here. So the inputs were binary, true, false, and the activation functions were threshold functions. So very simple type because, but then they were trained using sigmoids and converted to threshold before they were compiled. So that's one class that we looked at. Very, very simple type. Actually, I may even have a picture. Let me see. Do I have a picture for one of these guys? Yes. So this is, yeah, so binary inputs and step activation functions.
Okay. Okay. While we receive more questions, I have a couple.
Okay.
One, in terms of the properties you need of the circuits, how much of the possible Bayesian network models can you cover?
So to do probabilistic reasoning, which is just marginal probabilities, you just need decomposability and determinism. And basically that will do it. And if you want to do more complex queries like value of information, which I mentioned, like the same decision probability, then you need, at least the way we know how to do it is we would need to require stronger properties than decomposability and determinism. Yeah. The most common type that's used today is just determinism and decomposability. If you're doing things like sampling or computing marginals. And the most common type that's used when you're doing learning is the SDDs or PSDDs circuits. These also have properties, for example, that allow you to learn closed form maximum likelihood parameters under complete data and so on. So I gave you those main circuits earlier.
Okay, so but in practice, Bayesian networks will satisfy these properties, or we need to generate?
No, we have to make them. I mean, we take the Bayesian network, we write out the Boolean formula from it, and then we try to compile that Boolean formula to enforce these properties.
Okay.
We have to enforce them. That is what is the thing you need to do computation. And since we're on the subject, let me mention, even though this started by applying these to Bayesian network inference, where they're using more broadly, because this method that I showed you works for not just Bayesian networks, for many other things. People are using it, for example, in probabilistic programming, probabilistic logic programming. Typically, when you do not have a long tradition of dedicated algorithms, you use these approaches, which fall under what people call reduction approaches. That is, I have a problem. I don't want to invest in building algorithms for it. Is there a box where someone invested in that I can use to solve the same problem? This is what people do in satisfiability. So SAT solvers are meant to be used more broadly. You have an NP complete problem, then you try to see how you can rewrite it into a SAT problem, and then you run the SAT solver on it. Similar phenomena is happening here. I want to do, let's say, this kind of a reasoning. I don't have a dedicated algorithm. Let me go write out a Boolean formula, compile it into a circuit of the appropriate type, and then I'm done. So you're capitalizing on boxes that do compilation. So in a sense, this notion of taking a Boolean formula and compiling it into a circuit of an appropriate type is similar to basically doing set solving, but set solving was doing it for NP. This guy is doing it beyond NP.
Okay, we have some more questions now. So one is from Arturo Hernandez. Could you use this explaining approach to find or identify the faulty gate in a large combinatorial circuit?
Yes. And in fact, if you go to my course, last week, you'll find a lecture called Model-Based Diagnosis, in which we discuss this. What happens there, and I'll give you, subscribe to the channel. So what happens, I'll give you the gist of it. You take a Boolean formula that represents your circuit, and you end up representing whether a gate is faulty or not using another variable. And once you give me a system observation that is abnormal, I can generate a tractable circuit that captures precisely the reasons that or what went wrong. And then you can use that circuit to do things like find the state of the system that can explain the abnormal behavior while having the smallest number of faults. It's called min cardinality diagnosis. Yes. In fact, frankly, that was one of the earliest applications of tractable circuits. I used to work in that area of model-based diagnosis a while back, and this was one of the first applications, even before we used them to do probabilistic reasoning. So a lecture called Model-Based Diagnosis, and it should have been last week on the YouTube channel, Automated Reasoning Group, UCLA.
Okay, another question from Sebastián Bejos. He's asking if there is reduction from continuous circuits like Gaussian networks for this kind of circuits.
I don't know about a direct reduction in that sense, but I have to tell you that for the arithmetic circuits, people have been using that. So the weights of these circuits, I put numbers, and people have been putting distributions as weights. So they have been combining them with continuous variables. The one thing you have to realize that this notion of decomposability and determinism is, in a way, transcends things, because it's about variables and whether a system you have that you broke into two parts, whether the two parts share variables or not. And it's independent of whether these variables are continuous or discrete. These properties, if you think about them very deeply, decomposability is about decoupling. I want to take a problem and break it into pieces that do not interact. This notion of do not interact based on a variable is orthogonal to what that variable is, whether it's discrete or continuous. The other notion, determinism, if you think about it deeply, what is it? Determinism is case analysis. I want to take a situation, I want to say, I want to analyze it by breaking it down into this case or that case. And I don't want these two cases to overlap, right? Alpha or beta. Again, this notion of mutual exclusiveness is broader than simply discrete variables. So I don't know specific context you have, but I can imagine that you can use these ideas in continuous settings.
Okay. Someone is asking where can you find the lectures you mentioned?
How what?
Where are the lectures? Maybe the address of
the lectures. I don't have the URL, but here is the YouTube channel. If you go ahead to YouTube and just type UCLA Automated Reasoning Group in YouTube, you should get to this channel. And these are just some of the lectures. I think in an earlier slide, let me point you to the earlier slide where we had here they are. Okay, the courses, you'll find the lectures that look like this, but let me show you what you need to look for in particular. Okay, sorry, I'm going, it's a lot of slides. We went through all of this. Okay, here it is. This is the main YouTube channel. And if you scroll down, you're going to find this automated reasoning. This is the course. And this is a playlist. And then learning and reasoning with Bayesian networks, that's another course. That's a playlist. And you will see these lectures that I was referring to. I hope this, yeah, but just on YouTube, just type UCLA Automated Reasoning Group. Okay, someone found it. So that's not me doing this. So someone is actually showing people the page. Very good. Thank you. Very good.
Yes, I think
You have a fantastic team here.
Yeah, yes. Well,
All right.
I don't see any more questions. So maybe okay.
Someone is saying, is there some relation to the area of model checking? Of course, of course. So model checking studied some of these circuits. I skipped OBDDs when I talked about these, and the people in model checking basically subscribe to the same methodology, but not in such a general way. They've mostly used OBDDs to do model checking. And if you know, one of the issues there is that these circuits would grow too much, the size of the OBDDs, and then they switched at some point to SAT-based solvers. In our hierarchy of knowledge compilation map, you can see that OBDDs are the kind of the least succinct. So if you go down, as you go down, you're adding more and more properties. You're getting more power, but things are getting larger. So model checking initially was using this, and these are too big, and you don't need them. So for example, if you're doing probabilistic reasoning, it's sufficient to use that, right? And there's SDDs here. And there was just like a recent paper like a couple of weeks ago about doing effectively model checking using SDD circuits. So that's the interaction. Yes, they have used specific types of tractable circuits initially. Any other questions?
Well, I have another one.
Sure, sure.
So you were talking about learning directly these circuits, and then you can kind of inject some knowledge, like restrictions. My question is, can you inject knowledge related to independence relations?
So if there's different ways of constructing these. If you go back to this slide, you're still seeing my slides or no?
No.
Okay.
Now we are.
Good. So these circuits are constructed in different ways. In this slide shows how you can compile them from a Bayesian network model. In this case, yes, they do actually contain the independence relations of the Bayesian network in this case. And there was the other way of constructing them, which is hands-off, like in this example. In this example, there is no Bayesian network, right? In the sense that I just have logical constraints and data. Okay, that's the other extreme. But there is a place in between, because this is now, yeah, you cannot have independence and so on. You just have logic. Now, let me show you the slide that I skipped, because this is important. This is the notion of structured Bayesian networks. Jason Chen, a PhD student, just graduated this summer, is currently at Waymo, did his thesis on this. This was meant to be middle grounds between Bayesian networks and completely free, just logical constraints. So what's the basic idea here? The basic idea is that in a Bayesian network, you usually have a single node, a single variable per node. This guy, every node has a whole bunch of variables. So what that means is the conditional independencies of the Bayesian networks apply to groups of nodes, but we're silent on what happens within each group of variables. Because sometimes it's not easy to come up with a Bayesian network when you put every variable as a node, right? This allows you to do something at a higher level. And let me show you, because this is a very cool application. What is this structured Bayesian network doing? It's capturing a hierarchical map. The idea is when you're navigating a region, your navigation in that region is independent of how you navigate another region once I tell you how you cross between them. So if you're going from Mexico to the United States, and once I tell you how you're going to do that, or between two states here, once I tell you how you're going to cross between them, what you're going to do on this side is independent of what you're going to do on that side. And this is capturing that. And it's saying, for example, if you tell me what the value of E1, E2, how you're crossing between these regions, navigating between Santa Monica, Venice, Westwood, Culver City becomes independent. And if you further tell me how you're navigating Westwood, then how you navigate UCLA and Westwood become independent. This allows you to go on one extreme to Bayesian networks, on the other extreme to the traditional PSDD framework. And how you specify the conditional distributions between one of these guys and its parents, that's this notion of conditional PSDDs, which I did not talk about. Very sophisticated representation for capturing conditional distributions that are used in the context of structured Bayesian networks. It was a long answer, but because I didn't cover this topic. So this is very recent, just the last couple of years.
Yes, that's very interesting. Thank you.
Sure.
There's one more question from Nicandro. As far as I understand, the variables in the examples are binary. What happens when we have variables that are not binary?
They don't have to be binary. Binary simplifies the discussion because we stick to Boolean circuits and so on. If they're discrete, that's fine. I'll give you an example. When I showed you this reduction from Bayesian networks, let me see. Yeah, this slide here. So this reduction from a Bayesian network to a Boolean formula assume that the variables are binary. They don't have to. They could be discrete, and the reduction will be a little bit different, but it works. And actually, those reductions in my book, I mean, Enrique mentioned my book on Bayesian networks. There is a chapter dedicated to these, and you'll see these discussed there as well. Yeah, we're just sticking to binary just to simplify the discussion. And here, I think, yeah, so go ahead.
Okay, I think there are no more questions. Last chance. If there are no more questions, well, thanks very much again, Adnan. Very, very interesting talk and very, very wide implications.
Thank you, Enrique. All right, thank you, and thanks everyone again for inviting me and for all of the great questions.